the important topic of hemodynamics. As a clinician, I need to understand what are all the factors that affect flow. And this brings us to the very important formula, Puzel's equation. Mr. Puzel, and I hope I'm pronouncing his name right, helps us to understand, physicists help us to understand all the factors that affect flow. And he has derived this famous formula which states that flow is equal to pressure gradient over resistance. P1 minus P2 is delta P, or pressure gradient, over resistance. Of course, we know that pressure flow, P1 is upstream pressure, P2 is the pressure at the end of the vessels, and resistance is the resistance in the vessels against flow. I do recommend that you familiarize yourself with this formula. This formula is the bedrock of peripheral circulation, and we will now use this formula throughout, and you will hear me referring to it all the time. Now, here is a single vessel. If this represents P1, flow is going into the vessel, and P2, flow is coming out of the vessel. Here is pressure at the beginning of the vessel, and P2 represents pressure at the end of the vessel. Therefore, pressure gradient will be P1 minus P2. This is pressure gradient. Resistance, of course, will be the resistance throughout the vessels. And therefore, this is what Mr. Puzel is telling us, that the flow is pressure gradient over resistance. Let's apply this. Let's apply this in terms of a real situation. Of course, we can rearrange this formula to find out about resistance. And we can see, therefore, that resistance is inverse to flow. Of course, if we keep pressure gradient, if we keep delta P constant. Therefore, the single most important factor that can affect flow is resistance. Because of this, now we turn to the physicists and we ask, what factors affect resistance? And they told us that resistance is proportional to VL over radius to the fourth power, where V is viscosity, length L of the vessel, and R radius of the vessel. So therefore, we now have all the factors that affect resistance and flow. Let us rewrite this. We are saying so far, according to Mr. Puzel, that flow is equal to delta P over R. Mr. Puzel then tells us that R is equal to VL over radius to the fourth power. In other words, he's saying that resistance is proportional to viscosity. If resistance is proportional to viscosity, resistance is then proportional to length. And he's also telling us that resistance is inverse to radius. But not just radius, but radius to the fourth power. These are the three important relationships we can derive from this equation about resistance. Now, let's look at each one of them independently. Can you tell me clinically of a condition where we have an increase in viscosity? Where we have an increase in viscosity. Quite naturally, you are thinking of polycythemia. Very good. So what would you expect to happen to the resistance in a patient with polycythemia? You will expect the resistance to increase. Can you tell me of a clinical condition where we have a decrease in viscosity? Are you thinking of anemia? That's right, anemia. Therefore, because of this relationship, we can say that resistance decreases in anemia. Now, let's put it all together. Mr. Puzel said that flow is inverse to resistance, and resistance is proportional to viscosity. Therefore, whenever we have an increase in viscosity, we are going to have an increase in resistance. Therefore, we are going to have a decrease in flow. This explains why a patient with polycythemia predisposes to thrombosis. That's a good concept to bear in mind. This also explains why a patient with anemia will have a decrease in resistance and therefore an increase in flow. Now, if we have an increase in flow, what does this mean? This explains why in anemia we expect the patient to have a hyperdynamic flow. Hyperdynamic flow. In other words, this explains why a patient with anemia, if you listen with a stethoscope, you can hear the fast rush of blood through the vessels. You can hear almost a bruit as the blood rushes through the vessels. Now, we said that Mr. Puzel, for the clinical application of this formula, he said that flow is equal to delta P over resistance. He told us that resistance is proportional to VL over radius to the fourth power. Now, clinical application. We have a patient, Mr. Jones. And Mr. Jones, during investigation, was found to have a 50% occlusion of his left anterior descending artery. What is the clinical application of this formula that we have learned? Now, if Mr. Jones has a 50% occlusion of his left anterior descending artery, the exam will want us to know, how does this affect flow through the left anterior descending artery? We are halving the radius of this vessel. So radius is down by half. Mathematically, therefore, when we are dividing an index by a denominator, we will take the denominator and multiply it by itself to the value of the index. The value of the index is 4, so therefore the denominator is 2. We multiply 2 by itself 4 times, which will now give us 16. What does this mean? It means that the resistance will increase 16 times. So that's a massive increase in resistance. What should we expect to happen to flow? A decrease by 16 times. Now, take note of this. We decrease the radius by half, but therefore we decrease the flow not by 2 times, not by 4 times, but by a massive decrease of 16 times. This is the importance of Puzel's equation. Now let's put it all together. Fortunately for us, before I move on, the USMLE is not a mathematical exam, it's a conceptual exam. So 99.9% of the time, when they're asking you to relate radius to resistance and flow, they are going to say that the vessel is 50% dilated or 50% constricted. Therefore, the magic word is always 16. Imagine our mathematical horror if they say the vessel is 26% occluded. We will need a computer and possibly still get the math wrong. But therefore, they are very kind and they will tell us 50%. Now, all I have to pay and you have to pay attention to is it dilated or is it constricted? So therefore, the flow will be 16 times increase or 16 times decrease. Now, let's put this formula all together now and make some conclusions. We started off with the bedrock formula where Mr. Puzel taught us that flow is delta P over R. He went on to say that R, resistance, is equal to VL over radius to the fourth power. Now let's put it all together into one equation. We can now say that flow is equal to pressure gradient times radius to the fourth power, when we flip it around, over VL. This is something that you must remember for your exam, this formula. In one formula, we relate all of the factors that affect and influence flow. This is the clinical importance of this formula for Puzel. Now, let's continue and look at the other slide. Let us look at the effect of hematocrit on blood viscosity. As you can see in this graph, Normal hematocrit is expected to be about 40%, and therefore at about this, we will expect viscosity to be roughly around 3 units of viscosity. As you can see, as you increase hematocrit, polycythemia, you are increasing viscosity. And of course, as you increase hematocrit, you increase viscosity, what will you expect to happen to flow? That's right, flow will decrease. Because remember, we related flow is inverse to resistance, which is proportional to viscosity. And of course, if we decrease hematocrit, as would happen in anemia, as we said before, what would you expect to happen again now to resistance? Decrease, and viscosity will decrease and flow thereof. Very good. Now, when we are talking about flow, according to the pathologist, flow can be expressed in 2 ways. When blood is flowing through our vessels, it's either laminar flow or turbulent flow. Laminar flow or turbulent flow. What is laminar flow? According to the pathologist, blood has a tendency to flow in layers. And because it has a tendency to flow in layers, again, because of this formula, flow is equal to delta P over R. And where is that resistance coming from? It's coming from the walls of the vessels. So where in a vessel would you expect the greatest resistance? Of course, along the wall of the vessel. Where would you expect to have the least resistance? Away from the wall of the vessels. So wherever I have least resistance, I will have the greatest flow. And therefore, by logic, we are saying that the least resistance is away from the wall. And away from the wall is towards the center of the vessel. And that explains why in the center of the vessels, I will have a greater or a faster flow as opposed to along the wall of the vessel. This is called laminar flow. Anything that interrupts this will give me turbulent flow. Turbulent flow is interruption of the smooth layered flow of blood in a vessel, as would occur, for example, in a stenosed vessel. Anything that interrupts the smooth flowing of the layered flow. We now want to talk about Raynaud's number. Now, what is Raynaud's number? Raynaud's number helps us to understand whether we have laminar flow or turbulent flow in a vessel. How do we calculate Raynaud's number? Raynaud's number is equal to diameter times velocity times density over viscosity. Now that seems complicated. And you're asking yourself, how can you ever remember this? Very simple. Just remember that viscosity is the denominator. What is viscosity? The heaviness of a fluid. Viscosity, the heaviness of a fluid. If a fluid is heavy, what will happen? It sinks to the bottom. Viscosity sinks to the bottom of the formula. It is the denominator. Now you put everything else on top. There is no memorization here. And that is the formula, as if when you calculate the Raynaud's number, it comes to more than 2,000 units. That tells us that there is turbulent flow in the vessel. If it is less than 2,000, that tells us it is laminar flow. Very often the USMLE, they may not ask you to calculate it. They know we are physicians and not mathematicians, but they may ask us to interpret Raynaud's number. They may give you the Raynaud's number and ask what kind of flow will be expected in the vessel. As you can see, what we need to remember, the cutoff point is 2,000 units. What kind of flow is found in series or in parallel? What kind of flow do we have? What do I mean by that? Let's go back to the original formula. Flow is equal to delta P over resistance. We looked at the factors that affect resistance. Now, physicists have told us that whenever there are resistance in a vessel or in anything against flow, blood vessels, flow in electricity, flow in water, in a pipe, wherever there is flow. Whenever there is flow, there is resistance to flow. And these resistances or resistors can be arranged in two forms or two ways. in series or in parallel. In series or in parallel. So whenever and wherever there is resistances are arranged in one of two ways. Now, why do I need to know that as a clinician? I need to know it because it affects flow. And therefore, I need to understand how flow is affected in my patient's body. So let us look at series and parallel resistances as it exists in the body and apply physics to this concept to understand flow in our patient's body. We said that whenever there are resistances, it can be arranged in one of two ways. What are these two ways? Series, parallel. Now let's go into a little more detail. Try to understand what is series and what is parallel. What is series and parallel? Now, series. Before we look at the slides, series. There are two important things you must remember when someone mentions series resistances. First, you must remember that in a series system, flow is dependent. Now, what do we mean flow is dependent? We mean that flow must be equal at all points in the system. Key word, equal. So therefore, in a series system, flow is equal at all points. What else must we remember about a series system? We must remember that the total resistance in a series system is equal to the sum of the individual resistances. The sum of the individual resistances. What do we mean by this? Very important. In a series system, the total resistance is always greater than any of the individual resistances. The total is always greater than any of the individual. That's logical because the total is the sum of each one of them. All right? So, let us now understand this further. We are saying that the total resistance in a series system is the sum of individual resistance. Good. We are comfortable with that. We are therefore saying that the total resistance is always greater than any individual resistance. So we are comfortable with the second point again. And of course, in a series system, as we add resistances to the system, the total will increase. The total will increase. Now, this takes us to understanding parallel resistances. What do we mean by parallel resistances? And what do a parallel resistance look like? A parallel resistance, we can say, looks like, if we are to draw it so you can have a quick idea of it, if this represents a parallel resistance, here is pressure in and pressure out. Let's say this is resistance 1, resistance 2, and resistance 3. Now compare this to what we did in series. In series, we said that pressure in, pressure out, and this is R1, R2, and R3, the three resistances. Notice in series, the flow is going from one to the other to the other. Whatever goes through 1 goes through 2 and goes through 3. Is that the same in parallel? Look at the diagram for parallel. I know it's a long time since physics. Is the flow through R1 going through R2? No, it's independent of R2. The flow that goes through R2 does not go through R3. They are independent of each other. So therefore, what are we concluding? Right away, we are concluding that in a parallel system, flow is independent. Flow is independent. What does that mean if flow is independent? Does it have to be equal at all times? No, flow is not equal. Flow is not equal. Now, how do we calculate total resistance in a parallel system? Remember when we did total resistance in a series, we said that the total resistance is a sum of the individual resistances, and therefore we said that the total resistance is always greater than any of the individual resistances in series. Does the same apply in parallel? Not necessarily so, not at all. Because if you remember in physics, when we are going to do parallel resistances and the sum of parallel resistances, how do we go about it? How do we do the math? You remember from your days in physics, the dark days of physics, that in a parallel system, we calculate the total resistances in reciprocal. What do we mean in reciprocal? Of course, we will have to put 1 over RT is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Now, let's suppose we give values to these resistances. Let's suppose we say that R1 is 1, and R2 is 2, and R3 is 3. What's the total resistance in this system? Is it 6? Not really, it's not. We have to apply it. We have to say 1 over RT is equal to 1 over R1. What was R1? 1 plus 1 over R2. What was R2? We give it a value of 2 plus 1 over R3. And what was the value we give? 3. Now, back to 5th grade math. It's been a long time. Do you remember how to do fractions? Can you add this fraction? What did you come up with? Did you come up with 3 over 6? Well, if you did, you are forgetting how to do fractions. It is not 3 over 6. We have to always have the common denominator. 6 plus 3 plus 2. 1 over 1 is 6. Half is 3 over 6. And 1/3 is 2 over 6, which will give us 11 over 6. So therefore, 1 over RT is 11 over 6. To get RT, we have to flip this equation, which will now give us 6 over 11. Now, ladies and gentlemen, you are looking at something very miraculous and fantastic. What do I mean by that? We've added 3 resistances, each one valuing R1 is 1, R2 is 2, and R3 is 3. And what is our total resistance? Our total resistance was or becomes 6 over 11. Very important. Notice, is 6 over 11 less than 1? Yes. Less than 2? Yes. Less than 3? Yes. So therefore, this brings us to that important conclusion. In parallel systems, the total resistance is always less than any of the individual resistances. This is a very important conclusion. The total resistance is always less than any of the individual resistance. So let's put it together now. We are saying series, total resistance is more than the individual resistance. Parallel, total resistance is less than individual resistance. This represents the most important difference when systems are arranged in series or arranged in parallel. When systems, because of this fact, we can say that the flow is equal. And because of this, we can say the flow is not equal. Which brings us then clinically to why, as a physician, I need to know the difference between series and parallel. And we will now apply that clinically in terms of a patient and how does the different parts of the body, this arrangement affects flow. So the question we want to ask ourselves is, in the body, where do we have series and where do we have parallel resistances? And that's the next question that is important. And then we are going to look at how does this affect the flow in those different parts of the body. Now, series. Where would you expect series? Most series flow is, we can describe it as being within organs. Most parallel flows we can describe as being between organs. In other words, in a simple way, we can say that series flow are intra-organ and parallel flow are inter-organs, between organs. And therefore now we are going to look and understand why we have this arrangement in series and in parallel. So in this slide, we are going to demonstrate what we mean by in parallel systems, the flow is between organs, or the resistance are arranged between organs. As you look at this slide, you will see, for example, that we have our organs, whether it is the kidneys, the intestines, whether it the endocrine, muscle, these are all arranged in parallel. So all our organs are arranged in parallel. And to demonstrate in a simple diagram for us, we can say, for example, if I'm to illustrate, again with parallel, if this represents the parallel system, we can say this represents, for example, the GI tract, this represents the kidney, and this represents the musculoskeletal system, and etc., endocrine, and so forth. So all of our organs are arranged in parallel. And we said that in a parallel system, to emphasize, we said that the total resistance is always less than the individual resistance. Now, what's the clinical benefit of learning this? What can the exam ask us on this? One of the questions that can be asked of us here, for example, is if a donor, a young woman, donated a kidney to her sibling, to her brother, what impact would you expect this to have on the resistance in her body, flow in her body, cardiac output, and heart rate? Let's put that down. For example, a young woman donated a kidney to her brother. The exam, they love to put the questions in this format. What would you expect to happen to the resistance in her body, the flow in her body, the cardiac output in her body, and heart rate in her body? And the question will be, of course, those famous questions that we all love, with arrows going up and down and everywhere. And you know how those arrows give us whiplash injury, for example. So if you're in the question right now, if you're in the exam right now and you see this, what would be your choice if I give you, for example, resistance goes up, flow goes down, cardiac output goes up, heart rate goes down, for example? Let's say we were in the exam and we see something like that. For example, I hope I have the right answer there. I'm not too sure. We'll work it out. This is the typical way they present this question. So let's approach it. In order to approach it, we have to bear in mind that this young woman donated a kidney. So right away, is a kidney an organ? Of course, we are talking about an organ. She donated a kidney, so what has she done? She has subtracted an organ from her body. She has taken away an organ from her body. How will this affect resistance in her body? Here are two principles I want you to remember at all times. When we are talking about the parallel system, we must remember, in the parallel system, as we add resistances, this would lead to, as we add, the total becomes less. In other words, you add to get less. That does not seem mathematical, but we are dealing with parallel systems. The opposite of that is true. In a parallel system, as you subtract resistances, the total resistance will increase. The total resistance will increase. In other words, I want you to always bear this in mind. In a parallel system, you add to get less, you subtract to get more. Now let's apply this principle to what we just did. If this young woman donated a kidney, an organ, is she adding an organ or subtracting an organ? Of course, she's subtracting an organ from her body. And if she's subtracting an organ from her body, according to our principles, what would you expect to happen to the total resistance? You subtract to get more. You subtract to get more. So her resistance goes up. So therefore, if her resistance goes up, what will happen to her flow in her body? Resistance is inverse to flow. If flow goes down in her body, what is the source of flow? Cardiac output is what puts blood into the system for flow. So therefore, in order to have a decrease in flow, what will happen to her cardiac output? It will decrease. We all know that cardiac output is equal to stroke volume times heart rate. For the cardiac output to go down, what must happen to heart rate? Heart rate must go down. So therefore, this young woman would have a bradycardia that is normal for her. In other words, this bradycardia is normal for her. Why is this so? Well, and this is important because if a physician is not remembering his physiology and the patient comes in with a case and during examination she has bradycardia, of course, quite naturally, patient with bradycardia, especially if Mrs. Jones, who donated a kidney, is complaining that she's been putting on weight over the past couple of weeks. And during history taking, she said a year ago she donated an organ, but the surgery was fine and she's fine. She has all the medical records to show she has recovered fully from the donation. But over the past couple of weeks, she's been putting on weight. Mrs. Jones is worried about that weight gain. And during examinations, you found that she has a bradycardia. Immediately, what do you think about when you see a patient with bradycardia who has been putting on weight? That's right. The next question you will want to ask her is, Mrs. Jones, are you feeling cold? And of course, she's in the clinic and the AC is on, and she will say what? Yes, I do feel cold. And right away, as a young physician, what will be your conclusion? Patient has bradycardia, putting on weight, feeling cold. Yes, you will think of hypothyroidism. But be careful now. We have to remember her physiology. That bradycardia is not because of hypothyroidism, but most likely consequent to the fact that she donated an organ sometime in the past. So we have to be careful, and that's why the exam wants us to be aware of these circumstances. Now, another way to rationalize this, to understand this well, Mr. Puzel said that flow is equal to delta P over resistance. Let's extrapolate his formula to include the whole body. This formula represents only a blood vessel. What about if we are going to talk about the whole body and apply this to the whole body? Flow in the whole body, of course, is cardiac output. And in the whole body, delta P, the P1 and P2, the beginning of the system is the aorta. And where is the end of the systemic circuit? The right atrium, let's say. And resistance will be total peripheral resistance. We said that the mean aortic pressure is approximately, let's call that 93, and the mean right atrial pressure is approximately 0. So therefore, cardiac output is equal to mean aortic pressure over TPR. Why is that so? Because right atrial pressure is equal to 0. P1 minus P2 is equal to P1 because P2 is 0. So right away we come up with that very important formula that mean arterial pressure is equal to cardiac output times TP. TPR. I think everyone has memorized this formula and knows the derivative of that formula. We've also memorized, and we'll talk about this later on, but I want to use this to emphasize the appreciation of what happens to blood pressure when someone donated an organ. We know that cardiac output is equal to heart rate times stroke volume. Let's apply what we've just learned to this formula. This young woman donated a kidney. So therefore, we said you subtract to get more. So what will happen to her TPR? Her TPR will increase. Resistance increases. So therefore, if resistance increases in this formula, right away, what will happen to her mean arterial pressure? It will increase. So therefore, now the body will try to compensate. How will the body compensate? In order to bring the blood pressure down, it will have to decrease cardiac output. And how can the body immediately decrease cardiac output? By decreasing heart rate, thereby bringing the blood pressure down. The blue arrows represent the compensation that will take place consequent to the donation. As you can see, heart rate goes down. Why is it goes down? To bring the blood pressure, the mean pressure, back to normal. So therefore, this bradycardia is necessary for her to keep the blood pressure normal. This is one of the most important clinical reasons why we must understand the effect of series and parallel resistances on flow. I think that you are comfortable with that now, and we can now proceed to look at the other slides. Once again, in this slide, we are comparing two organs. As you can see, the flow is different in each organ. So we are once again establishing that the flow in parallel is not equal